Hello and welcome to Byju's JEE Advanced series. My name is Mrinal and the topic for today's video is kinetic theory of gases. So how we are going to go about this video is, first we are going to do a quick analysis of the questions that have appeared in JEE Mains and Advanced exam, and then we are going to solve some really good problems. But before doing that, for such amazing videos, please like and subscribe to our channel and don't forget to hit the bell icon. Let's first talk about JEE Advanced exam. So in 2018, just last year, one question was asked on PV diagram. In 2017, again one question was asked from PV diagram. 2016, there were no questions asked. In 2015, there was one question asked that was based on the gas laws. 2014, again, one question was asked from molar heat capacity. Now talking about mains, 2018, one question was asked from gas laws. 2017, again one question was asked that was from ideal gas equation. 2016, if you see, there was one question from PV diagram. 2015, there was one question from average speed and root mean square speed. And 2014, there were two questions that was from gas law and molar heat capacity. So overall, you can expect 1 to 2 questions in your mains exam, whereas one question is what you can expect in your JEE Advanced exam. So we all have come across an oxygen cylinder, right? So in this problem, we are given an oxygen cylinder. The capacity of this oxygen cylinder is 16 liters, okay? The pressure inside the cylinder is mentioned to us as 1.38 into 10 to the power 7, okay, pascals. And that's the gauge pressure. So gauge pressure is basically the pressure which is above the atmospheric pressure, all right? And the temperature is given to us also, that's 300 Kelvin, that is the room temperature, okay? Now, we are told that this cylinder is leaking gas, and the gas that is coming out at a rate of 2.4 liters per minute. So that's the volume flow rate that has been provided to us, okay? So the question that is asked from us is, how much time will it take for the entire cylinder to be empty, okay? So let us see how do we proceed with the solution. So in this problem, we first need to notice one thing. Which equations do we apply? Am I allowed to apply the ideal gas equation? Right. So ideal gas equation generally we apply when the number of moles are fixed. Is it fixed in this case? Can I analyze that? Yes, it is. How can I say that? Is that the total number of moles which were inside the cylinder are now outside, right? So essentially the entire oxygen molecule which were initially inside, the same number of molecules will be outside also, okay? So I can apply the equations, okay? So if I apply that, I can write the initial condition P1 V1 upon T1 equals to, let us say, P2 V2 upon T2, right? So P1 is the pressure in the initial condition when pressure is given to us as 1.38 into 10 to the power 7 pascals, okay? The volume we have to consider as the volume of the cylinder because the entire gas is inside the cylinder, and T1, the temperature is given to us as 300 Kelvin, that's the normal temperature, right? Now when this gas leaks out, it leaks out into atmosphere. So P2 will be, first the value of P2 will be equal to 10 to the power 5 pascal, that's my atmospheric pressure, right? And T2 is also the temperature at room temperature, so we'll again take it as 300 Kelvin. And V2, now V2 is what actually we have to figure out, right? So if I think about the volume, I have been given the volume flow rate, but I have not been given the volume directly, correct? So if you just think a little bit, volume flow rate is the amount of volume coming out of the gas per minute, right? That's given as 2.4 liters, right? So let us say if I assume the total time it takes for the entire cylinder to be empty is T, then the volume V2 can be written as delta V upon delta T times of this T, where T is this total time in minutes when my entire gas gets out of the cylinder, right? So I can write this as 2.4 into T, right? So I get my V2. Now, all I need now is to substitute these values back again in my primary equation. That's P1 V1 by T1 equals to P2 V2 by T2. So P1 is given to me, that's 1.38 into 10 to the power 7 pascal into V1 is of course the volume of the cylinder, oxygen cylinder, right? And that's given to us as 16 liters. So we'll take the same volume and we'll not change the unit into meter cube or anything. Why? Because on the other side also we are going to encounter liter, so they all will get cancelled out. So it's just unnecessary waste of time. So we'll not do that. We'll just write 16 and divided by 300 Kelvin, which is equal to P2. P2 is, of course, because the gas is leaking out into the atmosphere, so the pressure outside will be equal to 10 to the power 5 Pascal into V2. Just now we figured out V2, right? So V2 is 2.4 times of T, right? And this divided by 300. Yeah. So we got our expression. Now all we need to do is calculate and find this value of T, because T is what is asked in this question. So let's just quickly calculate this. This 300 gets cancelled, and if I write the expression for T, I can get this as 1.38 into 10 to the power 7 into 16 divided by 10 to the power 5 into 2.4, right? So now if I just cancel this 16 and 2.4, I get 4 times, this is 0.6 times. Now this 0.6 times, I can cancel this with 1.38 and I'll get 2.3, right? So I get this as 2.3 into 4 into, and this 10 to the power 5 and 10 to the power 7 gets cancelled out, and we get 10 to the power 2 into 10 to the power 2, right? So 2.3 into 4 will be equal to, well, that's equal to 9.2, and 9.2 into 10 to the power 2 minutes. So this is equal to 920 minutes, right? So 920 minutes is the total time it takes for the oxygen cylinder to be empty, right? So I have to convert this in hours, right? Why? Because the options, if you see, are all given in hours. So if I just divide this 920 divided by 60, that equals to, well, approximately, you can take it as, 15 hours, right? And 15 hours is my correct answer. So in this question, we are given a setup of piston cylinder assembly, and this piston is attached to a spring. All right, the spring constant of the spring is also given to us, and it is told that inside the cylinder there is an idle gas, and the pressure of the idle gas is P0, which is mentioned to be more than the atmospheric pressure. All right, now this piston has got some mass, and the whole setup is frictionless. Also, one important thing to note is that this whole system is thermally insulated, so we are not allowing any amount of heat transfer to take place between system and the surrounding, right? Now what is told in the question is that at equilibrium condition the piston goes up by x0. All right, and since this is the question having multiple options as correct, we'll check out each option one by one and try to figure out what is asked in each one of them. So let us look at the first option. So first option, if you see, is basically an expression of the final pressure of the gas. So we have to compute the final pressure of the gas, right? So if you look at this situation, if I draw a free body diagram of the piston during equilibrium condition, if you look at this piston, the forces that will be there are the force because of the atmospheric pressure, right? The force because of the pressure of the gas, the force because of the mass of the piston, and the force because of the spring. So these are all the forces. We will just draw a free body diagram and figure out that in equilibrium all the forces must be balanced, right? So if you look at the first force, that is the force because of pressure of atmosphere. So I can write this as PA times of S, and this will be downward direction, right? The force on the piston because of the pressure of the gas will be equal to P times of S. Then there will be a force because of the weight of the piston, and I can write that as mg. And also, since the piston is moving up, the spring is going to get compressed, and if the spring is going to get compressed, it's going to provide a force in downward direction, right? So there will also be one more force over here that will be equal to K times of x0, because x0 is the distance by which the piston moves. So we are pretty much sorted with all our force balance. So we have got 3 forces which are acting in downward direction and 1 which is acting in upward direction. So at equilibrium condition, all these must be equal, right? So if I write that expression, PS equals to PA times of S plus mg plus kx naught. This is my expression of force, right? But I need an expression of pressure, so I have to divide the entire thing by area. So S is the area that's given to us in the problem. So P equals to PA plus mg upon S plus kx naught upon S. So this is the expression of the final pressure of the gas that we have got. Now let us look at the option, and yes, it's the exactly same expression, so our option A is correct. So moving on, if you look at the second option, it's basically the expression of work done by the gas, right? So we have to compute an expression of work done by the gas, and then we have to compare that what is given in the option, is it correct or wrong, right? If I write the expression of work done by this gas, I can write it as PS times of x naught. That's the work done by the gas, but this work done will be done against three things. Number one is the atmospheric pressure. Number two is against the weight of the piston or the gravitational force, and number three is the spring force. So if I can write the expression, that is PAS into x naught plus mg x naught plus half kx naught square. So these are the three forces, right? And work will be done against all of them. So work done, this is the work done against the atmospheric pressure, work done against the weight of the piston, and work done against the spring, right? So I get an expression of work done, right? So this is my work done basically, and if I compare with the option, well, it does not match, right? So our option B is wrong, right? Now moving on, let's talk about the third option. So third option basically says that the internal energy of the gas decreases. Now this is quite interesting. If you notice that the whole system that we have taken is thermally insulated, and if our system is thermally insulated, the work has to be done at the expense of internal energy. So if the piston is expanding, the gas is doing some work, and if the gas does some work, it has to be taken from the internal energy. Hence, internal energy must decrease. So obviously option C is correct. And if you look at option D, it's all of above, which is obviously wrong because option B was wrong, right? So we have got correct options as A and C. So the question that is given to us is a very interesting problem, and it's also a very commonly occurring problem in your JEE mains and advanced exam, right? So in this problem, we have a vessel, and this vessel is partitioned into two parts, and let us call this as left part and right part, okay? Now both these parts are filled with two different ideal gases, all right? And the separator between them is a diathermic wall. So diathermic wall is a wall which will allow the heat transfer to take place, all right? Fine. So we are given that the RMS speed on the left hand side is equal to the average speed or the mean speed of the gas in the right hand side. So this is the condition that is given to us, and we are asked what is the ratio of the masses of the two sides, right? So we have to find this ratio, and let us solve this problem. So if you look at this part, the most important the most significant part of this problem is the diathermic wall, because this diathermic wall will allow the heat transfer to take place, and if the heat transfer takes place, then the temperature on both the sides is going to be equal, right? It's quite important for us, because as we put in the formula later on, you'll know that we can cancel this stuff, right? So we can write the RMS speed for the left hand side as VRMS equals to root over of 3 kT upon m mass on the left, right? So this is the formula for VRMS. Now of course we have got other formulas as well, but why did I select this formula in particular? The reason is because at the end I need to know the ratio of the masses, right? So I'll be using a formula which has mass in it, right? So in this formula, if you see, VRMS is equal to root over of 3 kT upon ml. This K is the Boltzmann constant, T is the temperature in absolute scale, and mass is the mass of the gas on the left side, right? And also if I write the expression of V average for the right hand side, because they are telling us that both of these are equal, right? So that value is equal to 8 kT upon pi mass on the right? So again, K is the Boltzmann constant, T is the absolute temperature, T is the temperature in absolute scale, and mR is the mass that is contained in the right hand side, right? So the condition is given to us. It's pretty straightforward, that the left hand side value of Vrms is equal to the right hand side V average, right? So I'll just equate it and I get 3 kT upon ml, which is equal to root over of 8 kT upon pi mr. Now if I square this expression on both the sides, I end up getting 3 kT by ml equals to 8 kT by pi mr, right? Now, as I have told you, since this is a diathermic wall, of course, both the sides, the temperature will be same, right? That's why I have taken T on both the sides. So basically this my KT and KT gets cancelled. So all I need is the ratio of ml is to mr. So if I just write this expression further, I'll get ml is to mr equals to 3 pi upon 8, right? So that is what was asked. So as you can see, 3 pi upon 8 is my correct answer. So if you look at this problem basically revolves around a molar heat capacity, all right? So we are told that we have a graph, and this is a PV diagram that is given to us, and it's a straight line and it passes through the origin. So that is what is told in the problem, and we have an expression of molar heat capacity, and that expression is given as N times of R, okay? So we have to find this value of n. Since this is an integer type question, so the value of n will be an integer, okay? So let us see how do we solve this problem. So if you look at the expression of molar heat capacity, it's given to us as C equals to n times of R, and this is the n that I need. Now for any general process or any polytropic process, the expression for C is written as R upon gamma minus 1 plus R upon 1 minus x, where x is that polytropic index, the power with which volume is raised to, right? Okay, so if I just compare both of them, I can write this as this equal to n times of R, and what happens is this, all this R gets cancelled, right? Now to find this value of n, I need to know the value of gamma, and I need to know the value of x. So for x, I need to get the expression for this process. So if I look at this graph, I know that this line is straight and it passes through the origin. This gives me one very important information, that P is directly proportional to V, right? Or I can write P equals to some constant into V, right? Or I can write PV to the power minus 1 equals to some constant, right? So if you talk about a general PV expression for a process, I know the expression is PV to the power x equals to constant. Now if I compare both of them, I end up getting my value of x equals to 1, minus 1, right? I end up getting my value of x equals to minus 1, right? So I'm sorted with the value of x. Now for gamma, it's told to us in this problem that it's a diatomic gas, and we know for diatomic gas the value of gamma is equal to 1.4, right? Now I just have to plug in these values and get the value of n. So I know n equals to 1 upon gamma minus 1 plus 1 upon 1 minus x, right? So if I just substitute that, I get 1 divided by, this is 1.4 minus 1 plus 1 minus of minus 1, that will be equal to plus 1, right? So if I solve this further, I get 1 upon 0.4 plus 1 by 2, right? And that's equal to, well, it's 2 plus 0.4 divided by 0.8. So that's 2.4 by 0.8, right? And that is equal to 3. So my value of n finally equals to 3. So in this problem, we have a diatomic ideal gas, all right? And we have been given the expression of pressure. It's a weird kind of an expression, all right? And they're asking us to find the expression of average translational kinetic energy, right, in form of P naught and V naught. They have also told that what will be this value of average translational kinetic energy when V equals to V naught, right? So when V equals to V naught, right? If you look at this problem, I want to know the expression of average translational kinetic energy. Now this average translational kinetic energy is slightly different from the other forms of energy that you go through in this particular topic, right? Like internal energy or total energy. You should not be confused by thinking that it depends upon the degree of freedom, right? Internal energy, total energy, yes, they do depend upon the degree of freedom, but average translational kinetic energy does not depend upon the degree of freedom. So if you're talking about one molecule, the formula for average translational kinetic energy is 3/2 kT in terms of a molecule. But when you talk about 1 mole of a gas, that is equal to 3/2 times of RT, right? So if I write, because since it's given that it's equal to 1 mole, so I can denote it by Ke, that's equal to 3/2 RT. That's for 1 mole, right? Now I don't know this expression of T. If somehow I'm able to get this expression of T, then I'll substitute it in this and then I'll get an expression for the average translational kinetic energy. How do I get this T? I'll use the previous conditions that's given in the question. So I have been told that the pressure is expressed in this form. P is equal to P naught. The whole thing is divided by 1 plus V upon V naught, and the whole thing is also cubed. Kind of a weird expression, but okay. We have also been told one more thing, that at V equals to V naught we have to find this value, right? So let us find pressure when V equals to V naught. So P equals to, I'll substitute P naught divided by 1 plus V, I can write it as V naught upon V naught and whole to the power 3. So of course these will get cancelled out and we get 1. So 1 plus 1 will become equal to 2. So I get that is equal to P naught upon 2. Now I have the value of P equals to P naught upon 2. Now if I apply the formula PV equals to nRT, I can write PV equals to nRT for P naught and V naught, because that is the condition at which I have to find the value. So I need the temperature at that point, right? So since the number of moles is equal to 1, I can write P naught V naught upon R equals to T, right? So I end up writing the expression for T, and T is what was required to be substituted in the formula of the translational kinetic energy, right? Average translational kinetic energy. So I can write K equals to 3/2 times of R into P naught V naught 2 times on R. So this R and R gets cancelled out and we are left with the final expression, that is 3/4 P naught V naught, and this is my correct answer.
For more videos and live lectures on the JEE, click on the subscribe button now.